Hey everybody, I want to show you a couple examples of some very common mistakes made when students try to do hypothesis testing. The first mistake I like to call the cart before the horse mistake, and it's due to usually poorly designed questions, right? For instance, this particular question was from an exercise where students were asked to go find a set of data, and then from that set of data, basically answer these questions, come up with some null hypotheses, and then run a test and check your hypotheses and all that kind of stuff. Well, the problem is that question itself is set up in such a way that it's almost forcing you to do a cart before the horse analysis. And what I mean by that is, in real life, you don't run a hypothesis test on data you already have, right? The idea is you first come up with a hypothesis, then you go out and gather data to enable you to test that hypothesis. Okay, so what a lot of students don't get is that a hypothesis test is really just a way of checking a guess. Your hypotheses, right, especially the null hypothesis, is an educated guess. You think something acts a certain way based on maybe previous knowledge or observation or just your gut instinct. And then you decide to test it. You come up with a theory. I think the world works this way. And then the alternative would be, blank. And now I'm going to go out and I'm going to find some data that's going to help me test this guess, and then I'm going to run the analysis on the data, and then based on the analysis, I can either reject or fail to reject my null hypothesis. But what happens oftentimes with these types of questions and these assignments is students go out and they find a set of data, and then they kind of run the hypothesis test on the data, or they run some summary statistics on the data, and they know something about their data set, and then they set up their hypotheses based on what they already know. And that's a waste of everybody's time because you already know that. You already ran the summary stats. There's no reason to run a hypothesis test, right? A hypothesis test is a guess about something you don't know, and then you go find the data and run the data and see if the data matches your guess. So you see how this is kind of a cart before the horse scenario here. And this is what happened with this student is they said, hey, I think the average price of a random sample of homes is this. Well, they got that because they obviously ran the numbers, because here it tells me that the sample mean, right, the average of my sample is that exact number that they're hypothesizing. So they set up their null hypothesis that the mean is going to equal that, and then they think, well, I think maybe the average should be greater or less than or not. It doesn't matter what the alternative was, whether they set it to not equal, less than, or greater than, they would have got the exact same p-value of 0.5. And the reason why they get a p-value of 0.5 is because the average of their sample is exactly what the null says it should be. And because it's exactly what the null says it should be, it sits right in the middle of their null hypothesis, right? What a null hypothesis does is it creates a distribution, right? So here's your bell curve. And every bell curve is centered right here, right? Here's the mean of my bell curve. Well, the null hypothesis basically delineates where this mean lays. Because remember, this sits on a number line. So this could be the number 3. This could be the number 3000, right? This could be -10. It could be 0.001, right? This could be anywhere on the number line, depending on what your null hypothesis says you think it is. Well, if you sit here and go, my null is that it's going to be this number, so it builds a normal curve centered on the number, right? 329.11, and then it builds a normal curve centered right there. So then you go and run the data, and the data basically says, hey, if you have a mean of this, and it lands right here, what's the probability, right? And then it asks this question, what's the probability that the mean is greater than that? So it basically says, what is all the area above this? And you go, well, it's half of the normal curve, so it's exactly 0.5. And that's why they get 0.5 as a p-value. Very common mistake. Happens all the time. You'll also notice that your t-stat is close to 0, right? This e to the negative 9 means it's a scientific notation, and it's times 10 to the negative 9. So there are 8 zeros and then this 9. So your t-stat is basically 0 because it's sitting here right at 0. It's sitting here right in the middle of your curve because you set up your null hypothesis after you already had your data. It's not what you want to do. Instead, if you really were concerned, I shouldn't say concerned, if you really were trying to test something about housing prices, right? You thought, all right, what's the average housing prices for houses in California? And I'm only choosing California because this student is talking about California, and I don't know if this data came from California or not. They might talk about it here more in the question, but who cares, right? So let's say you want to know what the national, you think based on your observation, you live in town X and you've looked around and you think the average cost of a house is about 250,000, right? And that's based on observation. You've observed this. You've seen houses for sale in your neighborhood for 250,000. Now you want to come up with a hypothesis. You hypothesize, though, that based on your intuition, that you live in let's say a less than fancy neighborhood. And so you think the average price is actually greater than that. So your claim, right? Your claim is going to be that the average price should be bigger than 250K. And that becomes your null hypothesis. Sometimes it's called HA, sometimes it's called H1, right? Sorry, did I just say null? That becomes your alternative hypothesis. You always try to set your claim as your alternative hypothesis. And so that's your alternative hypothesis. Now your null is always going to be equal to. Yes, some books would say, hey, if your alternative is greater than, then the null should be less than or equal to. That's absolute crap because you can't build one specific null curve if the null hypothesis is less than or equal to, because this would be equal to, and then less than would be the infinite number of curves, right, that would be less than it. So that's total crap. So if you ever see articles or books talking about, oh, well, it's now accepted behavior to make the null less than or equal to, those are people who don't understand how stats work. And that's total crap. It cannot be that. The null has to always be equal. So in this case, you would say, all right, the null, right, is going to be equal to 250K. Then, now that you have your guess, now you would go out and you would grab data and you would check your data. So you would go out and you'd get a random sample of data. And again, it would depend on, was your guess that 250 or bigger than 250 was the average of houses in your state, in your county, or in the entire United States, right? And then based on that, you would gather data from those areas, right? If you were just worried about your state, then you get a random sample of housing prices in your state. If you thought it was just for the county you live in, then you'd go out and get a random sample of housing prices in your county. If you thought it was nationwide, then you'd get a random sample of houses nationwide, okay? Whatever it is, you would get the proper data for that stuff. So let's just pretend that this student's data came from the state of California, and your null and claim are all about the state of California. So you would build your null hypothesis based on this 250,000. See, you have to come up with the educated guess before you run the data, because once you run the data, you've spoiled it, right? We know that the average of this sample is 383,000, which is not 250. It's bigger than 250, right? But you can't base your hypotheses on what you see from the sample. That's, getting ahead of yourself. So instead, you would build your hypotheses based on a null of 250. And then this 383, it's going to land out here somewhere. 383 is going to be somewhere to the right of it. I don't know exactly how far because I'd have to run the actual numbers. But based on how far it is, then this, right, alternative of being greater than is basically looking for the area in the tail above it and saying, what's that probability? How much area is it? That if 250 was the actual average, this is the probability of getting a sample from that population with an average of 383. And then that p-value would probably be small enough that you then could reject the null that it's equal to and support your claim that it's greater than 250, because 383 is quite a bit above 250. And of course, it depends on how big your sample is and stuff like that and what the standard deviation is. But again, I haven't run the numbers because I don't have the raw data, but I'm just saying, let's say that it was small enough, like it came out to be, 0.02 or something. There's a 2% chance of happening, or 1% or whatever. Then you go from there. I don't want to get into all that. Those are other videos. This video is just talking about the common mistakes. And the common mistake here is you cannot kind of run the data first and then base your hypotheses on your data. You're supposed to make a blind, wild guess first, then get the data, run the data, and see if your guess is correct or not. So now you're saying, well, how can I do that with these stupid questions that tell me to go find data first? Okay, well, think of a topic you like, and then go find data on that topic. And then before you run any statistics on that data, make a guess. Who cares if your guess is way off? That's not the point of this exercise. The point of this exercise is to go through all the steps of how a hypothesis works and how a hypothesis test works. So feel free to make the craziest, dumbest guess you can think of, then run your data and see if it supports it or not. Just remember some of the basics. The number one thing is the null has to be equals. It cannot be anything other than equals. And number two, your claim should always be the alternative. Most people don't claim something equals something. Now, there are cases where your claim is going to be the null because you just, gosh darn it, you think something equals something and you want to go test that. But that's a very weak test. A stronger test is when the claim is the alternative hypothesis, because just think about the language. We never accept the null. We either reject it or we fail to reject it. And I know a lot of you think failing to reject is the same thing as accepting. It is not. It's the idea of innocent until proven guilty, right? The null hypothesis is kind of like the defendant in a court trial. If you have enough evidence to prove beyond a reasonable doubt. Remember, we don't prove anything, but we have enough evidence to kind of believe it beyond a reasonable doubt in a court of law. And it's the same thing with statistics. We never prove anything. But if we have enough evidence to make a strong enough case, i.e. our p-value is so small that we don't think it could happen by pure chance, then we're able to reject that null. We're able to convict the defendant. Say, hey, there's enough evidence that we think you're guilty. We haven't proven your guilt, we just have enough evidence to think you're guilty. Whereas if you don't have enough evidence and you can't prove their guilt, they walk out free. But does that mean you've proven or accepted their innocence? No, you just didn't have enough evidence to believe that they were guilty, right? They're innocent until proven guilty. The null is assumed true until proven otherwise, and it's assumed true. It's not known to be true, and we don't accept it as true. We just fail to reject it. And I hope that makes sense to you guys, that there is a huge difference between those two. So when you're able to reject the null, you do that because you have enough evidence to do so. And when you reject the null in favor of the alternative, again, we don't accept the alternative. We're just rejecting the null and saying the alternative is more likely true. And when that happens, that's a stronger result than failing to reject, because failing to reject means we just didn't have enough evidence to prove anything. We're just stuck with our original guess. So that's why it's better to make your claim the alternative, because then if you can find enough evidence to reject the null and support the alternative, then you've found evidence to support your claim. If your claim was the null, then all you can hope for is that there isn't enough evidence to not support it, right? That there isn't enough evidence to support the alternative, and therefore, by default, your claim is held in place. You see how that's a weaker argument? So scientists always want to make their claim the alternative, because if you can reject the null, it more strongly supports your claim than if your claim was the null and you fail to reject. That doesn't really still, see, failing to reject, again, isn't supporting. You're not supporting the null, you're just failing to reject it. Whereas when you reject the null, you're supporting the alternative. Okay, so I know it's a lot of semantics, but that's how the world works and that's how statistics work. So don't put the cart before the horse. You've got to come up with a guess first, then go out and run it, and then see if your guess is true or false. Here's the other common mistake that I want to discuss. Take a look at this question and see if you can spot what's wrong. Okay, so the null hypothesis is the average height of a female is 65 inches. So if we wanted to write that in symbols, we would have mu equals 65 inches. Right? So the alternative is that the average height of a woman is not. That's totally fine, right? So far, the two hypotheses are okay. This is not equal to 65, right? Confirm the results, blah, 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 blah. These are just their critical values for running a z-test, right? And then down here's their z-stat, and here's their p-value. Here's their sample proportion. Here's the count and total and so on and so forth. All right, do you see the problem? What's the symbol for sample proportion? P hat. What's the symbol that we would use for the population proportion? Well, it would just be capital P. What's the symbol for a sample mean, right? Sample average is X bar, and then a population mean is mu. Are you seeing the problem now? Their data doesn't match their hypotheses. Their hypothesis is about means, averages, numerical data. However, the numbers they ran, the analysis they ran, was on a sample of non-numerical data. They ran proportional data. Look, they've got a sample proportion, and they have a z-stat because of that, right? Because proportions live on the z-curve, on the normal curve. If we were running averages, shouldn't it be t's, right? Shouldn't we be using the t-curve? Because we don't know the standard deviation of the population. We would only use the z-curve, we'd only use the normal curve if we actually knew the standard deviation of the population when we're dealing with means. And we don't know that. We never know that. That's just silly, right? So the problem here is their hypotheses don't match their data. One of two things happened. Either they had numerical data, and then they turned it into proportional data by basically saying, well, I'm going to turn it into yes-no data. And a yes is going to be whenever the data equals 65, and a no is going to be when it's not equal to 65. And out of a total of 428 heights, we're doing heights, 49 of them were 65 inches tall. That's legitimate. I mean, you can do that, but it's silly. Remember, there's a hierarchical chain for data. The best data we can use is numerical, continuous, regular, ratio level data. The worst data is qualitative data, words, because there's very limited things we can run on qualitative data. Basically, all we can ask is we can do frequency counts, right? So they've taken numerical data and they've downgraded it to qualitative data and turned it into a bunch of yes-nos, which is not the best thing in the world to do. Sometimes it's necessary for the certain types of analyses you want to do, but in this case, it's not. It would have been better to have run the data as numerical data, run a t-test on it, and use your actual hypotheses, right, of equal to 65 and not equal to 65. Or the second thing is, so that's either the first thing, either they downgraded their data, or the other possible mistake that was done here is that they actually had yes-no data, right? They had proportional data, and all they could run was proportional analysis on it and count up, how many yeses and how many nos there are and that kind of thing. Remember, the data doesn't have yeses and nos. You set yes, so you tell it a success is whenever the data equals 65, that becomes yes, and when it doesn't, it's a no. Same thing, you could have run it on political parties, and a yes could have been independent, and a no would have been everything else. Democrat, Republican, Green Party, whatever, right? Um, so yes and no just means success and failure when we're talking about proportional data. So either they downgraded it to that and basically coded everything and made all the 65s equal to yes and all the other things equal to no, or they had proportional data. They had a set of data that were just a bunch of yeses and nos or a bunch of somethings and somethings, and they had the wrong hypotheses. They need hypotheses to match it. So they either need to change their hypothesis and then talk about, instead of this, it needs to either be P is equal to something, and then P is not equal to something. Remember, you use you use P and not P hat because your hypotheses are always based on the population parameter, and the population parameter is P. P hat is what you get out of the sample, right? So either need to change our hypotheses to this, or they need to rerun the analysis on numbers and get the analysis with a t-stat, right? They would have a t-stat, they would still have a p-value, and instead of a sample proportion, they would have a sample mean, they would have their x bar, right? And instead of count and total, I think it gives them like standard deviation and maybe something else. I can't remember off the top of my head what the display is, but it doesn't matter. All you need is the t-stat and the p-value, and then you would determine whether or not you reject or fail to reject based on that. Okay, so those are kind of the two most common mistakes. The cart before the horse happens a lot. This one doesn't happen as much, but I did want to point it out that your analyses need to match your hypotheses, and both of those need to match your data. All right, I hope this helps.